Hi, welcome to my video on threshold potential. So in this video, we're going to be kind of re-going through how an action potential is formed using chemical electrical gradients, and also learning for the first time about the all or none response and how kind of the intensity of a response functions. So in the space provided in your notes, I want you to draw the outline of this graph. Okay, it might take you a minute, so you may want to just pause and do that first. Okay, once that is all done, I'm going to start to fill in the graph. So this graph is showing the membrane potential, the voltage on the membrane at any given time throughout an action potential. So we're going to start at rest at -70, and we're going to just draw a quick little loop-de-loop. So we're going to have a little blip and then a full action potential and then go back to rest. So I'm going to number this graph off. The first part, okay, this little blip on the graph is the second, going all the way up to +40 is the third, and then down is the fourth, and back to rest is the fifth. So we're going to talk about each part of the graph and explain kind of what's happening. If I zoomed in back on the actual membrane of the axon, that picture with the pumps and the channels, kind of what's happening at each stage. So I also wanted to point out the threshold line, which I'll talk about in a little bit. So in the very first part of the graph, when we see it hovering around -70, this is when both of the sodium and potassium channels are just slightly open. The sodium potassium pump is constantly working. In this case, at -70, the reason that we maintain that -70 voltage is because we always have more sodium on the outside of the axon membrane. So this would be at rest. Now what happens is we get a little bit of an impulse detected on the neuron. What that triggers is kind of a chain reaction of the sodium channels, but because the impulse was very small, the sodium channels only open slightly, changing the voltage only a little bit. Okay, it only comes up to about -60, it looks like. Because threshold, I put in between 50 and 60, it has to meet that threshold or nothing happens. So that's why it goes back down. So in the all or none principle, this is an example of none happening. Nothing is going to happen if we don't meet the threshold. The sodium channels don't open up enough for sodium to flood in enough to change the voltage enough for that chain reaction to occur all the way down the axon. So no action potential occurs here. It's not a big enough impulse to be detected. A large impulse then would maybe be occurring after this, okay? Maybe a different set of information happens. Maybe someone lightly tapped you the first time on your shirt, on your shoulder, and you didn't quite feel it. And the second time, maybe it went all the way, okay? Because they kind of hit you a little bit harder. So this time we have a larger impulse. So all of the sodium channels open wide, sodium floods in and shoots our millivoltage up all the way to +40, and that we have an action potential happening. So the all or none principle is we have two options. We have a big enough impulse that it goes all the way up to 40, or we don't have a big enough impulse and nothing happens. All or none. Those are my two options. Okay, I can't go half the way. I can't go a super, super high amount of millivoltage. I just go up to +40 or I don't do anything at all. Okay, those are my two options, and that's the all or none principle. The fact that I can't go kind of a little bit of an impulse. If it doesn't meet the threshold, nothing happens at all. Okay, in the fourth step, this is when we are going to get rid of the action potential kind of features of our membrane proteins. So we want to go back to normal, back to rest, so that we can receive another impulse when it's time. We don't want to always be an action potential because then we would be getting like tremors and stuff like that. So in order to go back to normal, we have to change the way that our membrane proteins look. So first we're going to close the channels for sodium. We're going to open the channels for potassium. And when those potassium channels open wide, potassium floods out because it's all built up on the inside. That's going to overshoot our millivoltage at -90. So that's what's right here. And then the pump's going to kick in and kind of slowly fix it back to -70. And that's when we're back at rest. So that once we get back to rest, that means that if another impulse comes along that's large enough, it will go all the way up to 40 again. Okay, it has to go back to rest in order to receive the impulses again. So that's kind of what's happening at the graph. I just wanted to add in the names of like rest and action potential and repolarization or recovery period. I just wanted to add those in. So number 1/5, we would call that neuron polarized because it's at rest. During number 3, that's where it's depolarized because that's where an action potential is happening. And number 4 is going through repolarization or the recovery period. So I just wanted to make sure we remember the names of kind of what was happening in our neural transmission video. So with that in mind, and this idea of kind of the all or none and having to meet threshold, I have a question for you. So how come when someone taps you versus if someone pinches you in the exact same spot on your arm, how come I can tell the difference? How come I feel that lighter touch if someone taps you versus a really, really intense pinch when someone pinches you with more force? Why does that happen? So I want you to answer that question right now. So the answer to this question is a little bit complicated, but first we have to remember that if I was touching the exact same skin on my arm, the same amount of sensory receptors on your skin would be touched. Okay? But the difference is if someone was tapping you, maybe only half of those sensory receptors actually get triggered to meet threshold and fire all the way up to positive 40. Okay, maybe all of your other sensory receptors don't fire, only half of them actually meet that threshold. So you're getting about 50% of the impulses going to your brain from that specific area of your skin, whereas maybe a pinch of that same area makes like 80% of your sensory receptors actually meet that threshold and fire the impulse to your brain. So your brain interprets it as, okay, I'm getting the same amount of sensory receptors in that area, but I'm kind of comparing half versus 80% in that moment. So 80%, because it's more information to the brain will be like, okay, this is a way more intense signal. Okay, we have to remember this idea of threshold and this idea of all or none. The only option is to go up to positive 40. So some people might think, oh, maybe it will just increase the millivoltage to like positive 90. That's not an option. Either it goes all the way up to 40 or it just doesn't happen at all. So in order for us to sense different like types of touch, we have to look at how many sensory receptors are being triggered versus how many aren't in that specific area, not how strong their millivoltage is, because you only have one option. Either it's positive 40 or it's still at rest. Okay, it's all or none. So that's kind of how that works. So hopefully this kind of brought a little bit of light to your brain of kind of, again, a review of the action potential, how that's kind of formed, talking about specifically what's happening at each part of the graph, and then also understanding intensity of response and all or none response. So if that doesn't make sense, please feel free to ask me any questions. If not, have a wonderful day. Talk to you guys later.